Let's take half an hour or so and think about impacts of climate change and see if we can get our heads around some possible solutions. We're all aware of fire, drought, hurricanes. So let's go through some of these examples and hopefully we can come up with some idea of solutions on the horizon to this problem. We've been through the fundamentals of climate change. We've got a bunch of case studies out there that deal with solutions, possible solutions. This presentation is meant to bring a few of those ideas together and explore a few others. One way that impacts of climate change are shown graphically is in the form of these three graphs. Upper left, plotted on the x-axis is temperature, y-axis is probability of occurrence. This curve right here is for the climate of a previous cooler world, let's say early 20th century, or 19th century, or 15th century. And then the situation in a warming world. Overall, we might predict that mean temperatures will increase, that new records will be set for high temperatures, and maybe that there won't be such cold temperatures anymore. But that doesn't factor in the reality of increased variance in climate. So that when you combine increase in mean with increase in variance, you get a combined effect of, yes, we still see extreme cold. Some will use that as evidence that climate change is not really happening. We see far more incidences of record temperatures, record-setting heat waves. Trying to walk through Gay Pride Parade in Paris when it's 40 degrees centigrade, toting luggage behind you. Festive event, but not exactly like probably would not have occurred in the previous world. Stretch of many days in a row of 40 degrees centigrade, basically 100 degrees Fahrenheit in Paris. Paris will also get some anomalous cold snaps still. One of the major consequences of global warming, or climate change, is the reality that sea surface temperatures are warming, and this is causing greater amounts of water vapor in the air over warm seas that is leading to increasingly stronger low-pressure systems, typhoons, and hurricanes. This is Hurricane Katrina from satellite, 2005. Shown here is some damage from Hurricane Katrina. Burst levees. Levees meant to keep floodwaters in the river, but eventually the pressure of the river is so much the levees catastrophically break. Widespread flooding. Many people, especially of lower economic means, less access to power, having no means to get out of this flooded city. Intense monsoons in Pakistan. We've talked about monsoons. Warmer water in oceans or seas will cause greater evaporation and deliver more moisture to land, often in catastrophic doses or extremely intense precipitation events. Tropical Storm Irene in Vermont, we've looked at this as a case study earlier. We saw how Otter Creek in Middlebury benefits from the ecosystem services of a very healthy, functioning wetland floodplain ecosystem. Not everywhere in Vermont benefits from that. Some places are in steep, narrow valleys where there are no wide, broad floodplains to absorb the floodwaters. Typhoon Haiyan, Philippines. Hurricanes of Southeast Asia. Hurricanes used as a term in the Americas mainly. Typhoon in Southeast Asia. Hurricane Mitch, 1998, Central America. Landslides, much like in Puerto Rico during Maria. Volcanic mudslide here. Vast destruction from winds and flooding. Hurricane Otto tracked across Costa Rica and Nicaragua in 2016, caused a volcanic mudslide from the flanks of Miravaes volcano in northern Costa Rica that took the lives of 8 people who happened to be in its path. This is part of the research that I've been working on with my colleague Guillermo Alvarado, trying to figure out when similar volcanic mudslides, known as lahars, have occurred in the past, using carbon dating trying to figure out if there's some kind of recurrence interval or if those previous events are tied into intense precipitation events that might show up in the geologic or archaeological record. Hurricane Maria, fall of 2017, September 2017. Impacts that affected humans on a vast scale, also affected ecosystems. El Yunque National Forest before Hurricane Maria. Hurricane Maria flattened so many trees and really dealt a heavy blow to the forested tropical ecosystem of the island. Hurricane Dorian. Satellite photograph that was taken about a week before Hurricane Dorian settled down over especially Great Abaco Island. Before, after. Sediment strewn all over the place. The island is now full of brown, exposed soils, eroded ecosystem. About 30% of the reefs were damaged in the Bahamas from this incredibly intense low-pressure system known as Hurricane Dorian. Folks from Middlebury College actually have studied the reefs in the Bahamas, and some of their work served as the baseline, the pre-Dorian baseline, for the impacts that occurred in Abaco. A paper came out in 2005, almost right after Hurricane Katrina, that to me really synthesizes and summarizes the effects of climate change on hurricanes. Will there be more hurricanes overall? Maybe not. But of the hurricanes that occur, categories 4 and 5, the most intense ones, are predicted both theoretically and have been observed empirically to be increasing in abundance. So overall hurricane occurrence may not be increasing, but the intensity of those that are forming does appear to be increasing. And this is a study that was done over a 25-year time period, broken into 5-year pentads, 5, 5, 5, 5, 5, 5, 5, so 24, 25 years. And yeah, you can see that the number of intense hurricanes, or the percentage of intense hurricanes, however you look at it, the number 4 and 5, the really intense high wind, intense precipitation hurricanes are increasing, and their ranges are increasing. Storms like Irene are more likely to reach New England than previously. A lot of this climate stuff and extreme events is about probability. I will read this. It's important to recognize that given the natural variability of the climate system, it is difficult to precisely attribute a single event like a hurricane, or even a larger long-term event like an anomalously warm year or a drought, to anthropogenic climate change. So, probability of intense hurricanes is greater now than it was in a cooler, lower CO2 world. We could say that. Was Hurricane Katrina caused by climate change? It is consistent with what you would expect of warmer sea waters evaporating and causing more intense storms. We can also examine trends. So the Meteorological Office of Great Britain shows that the frequency of intense precipitation events is on the rise. And these would be precipitation events that have, like this would be like the 100-year flood or the 100-year kind of precip event. Those events, the frequency of intense precipitation events is increasing. The trend towards more extreme rainfall events is one we are seeing around the world, says Julia Slingo, Chief Scientist at the Met Office of the UK. You can press pause and probably have to type that into a web browser or search for it. If you want to dig into the details, you can. It's not 1 in 100 year, it's a 1 in 100 day. So analogous to the 100-year flood, but more of like a 100-day rain event. You would probably expect 3 or 4 100-day rain events per year, but the number of those events is increasing. What do we see in this graph? We've got time on the x-axis from 1900 to 2017. Here's the web link if you want to dig into it, globalchange.gov. This is United States. the relative number of extreme precipitation events. 2-day precipitation events exceeding 5-year recurrence interval. The relative number of extreme events is increasing. Warmer surface waters, warmer seawater, causing greater evaporation, delivering more precipitation in intense doses than previously before. This is something we have to plan for. If we think about climate change, one of the factors is we have to deal with mitigation. We have to deal with adaptation. We have to engineer roads, drainage systems, so that engineered systems are able to deal with the increased load, so that the capacity of our infrastructure can deal with the increased doses of precipitation that we're getting in intense, short time frames. Extreme 1-day precipitation events in the contiguous 48 U.S. states, pretty similar. Overall upward trend. Some of the extreme cold and warm, both ends of the variance spectrum, can be explained by changes to the polar vortex. And I will draw your attention to this link up in the right, this Vimeo link. It's a link to a lecture that was given at the college in the fall as part of the Clifford Symposium by Jennifer Francis, a climate scientist at Woods Hole Oceanographic Institute in Massachusetts. And she explains how warming conditions in the North Polar region, in the Arctic, are decreasing the gradient between the thickness of air in the tropics and the thickness of the air mass in the poles. As the poles warm, the atmosphere expands a little, and that, to make a long story short, I mean, she gives an entire 45-minute or 1-hour lecture, but the changing gradient between temperature in the tropics and the poles, we know the poles are warming faster, and the decreasing temperature gradient and the decreasing gradient in the thickness of the atmosphere from equator to North Pole means that the polar vortex, this air mass that tends to circulate around the North Pole, tends to get these huge waves in it now at times, such that temperatures on the range of, what are we talking here? This is degrees centigrade. 30 or 40 below centigrade, occurring in temperatures that are normally Arctic temperatures, occurring way down into the United States. We in Vermont have felt some of these polar vortices before, these super cold airs that come down and maybe last days or even weeks, like 10 days or something. So this is the jet stream, the boundary between temperate mid-latitude waters and polar northern high-latitude waters. And normally it's got a boundary that's a lot more like this. And the boundary tends to be much more, like linear or whatever. Not linear, but doesn't tend to have these huge tongues coming down. So these tongues can bring incredibly cold air way farther south than normal. I was in Costa Rica in January of 2018, and it was anomalously cold during January of 2018, a year before this, because of a polar vortex that was pushing cold air way down. I mean, look at this. What is this is like -10 or -20 centigrade. 0 centigrade is 32 Fahrenheit. So we're talking about like minus 10 to 10 degrees below Fahrenheit or something like that. Way down here. But yet then look at this band of warm air. This is 10 centigrade, so it's about 50 Fahrenheit. Middle of winter time up in Alaska, you're getting temperatures of like 50 degrees Fahrenheit, 10 degrees centigrade. So part of the variance in the climate system, and part of what will drive some people to say it's colder than ever before, there's no such thing as global warming, is actually a product of global warming causing changes in the boundary between the polar front and the more temperate air that occurs to the south. And this is from a cool website called climatereanalyzer.org. Check it out if you want. Yeah, just a little bit more on the polar vortex. So this would be Normally, air circulates the pole and is separated from another air mass that's farther south. And the boundary would be called the jet stream. Kind of strong air currents occur there. But as the poles warm, this boundary here becomes much more wavy. And you can get extremely cold air plunging far south and extremely warm air reaching far north. This is going to melt permafrost. Poor development often exacerbates impact of climate change on coastal communities. This barrier island off the coast of Carolinas in the southeastern U.S. is just, waiting to be battered by a Category 4 or 5 hurricane. This sandbar here is shifting sands. It's not permanent. It's not a permanent geological feature. So part of adapting to climate change is finding ways to not develop like this and to even incentivize abandonment of developments like this for developments that are on more stable areas. Sea level rise. We saw evidence of sea level rise from gauges and so forth in an earlier lecture. Exactly how you forecast sea level rise well forward into the 21st century depends on many factors. But almost undoubtedly, low-lying flat coastal areas, Bangladesh being a classic example because it's very flat, slow, gently sloping plain upwards, eventually upwards towards mountains. The low slope of Bangladesh, the low flat slope of the eastern coast of the United States, the low flat slopes of many of the eastern parts of Central America are all prone to both just being inundated by sea level rise and being hammered by more intense storm surges. So Bangladesh is one place we would be concerned about, and we can see that it's not insignificant. Sea level rise of 1.5 meters would displace many millions of people. And obviously, not only in Bangladesh. There are cities all over the world that are at sea level for which 1 meter or 1.5 meters of sea level would be devastating. Yeah, and often impacts are interrelated, like native forest ecosystems that are now experiencing hot, dry summers, hotter and drier than normal, warmer winters, with invasive species that kill trees, and fire suppression that alters natural cycles. These ecosystems are poised to burn intensely. So fires in California of recent years, very intense fires in many parts of the world, are related to all these interrelated factors. For sure, climate change, hot, dry summers is a driving factor, but there are other factors as well that we need to be aware of. And yeah, we got to think about the ecosystem services of forests that are burning so hot that they may never return to their former state. And we need to think about the ecosystem services that might be lost or need to be replaced by our targeted, informed, knowledgeable efforts to reestablish ecosystems, functional ecosystems, where they have been affected by fire or other natural disasters. We need to consider an impact of climate change that is already happening. Projected latitudinal changes and also projected altitudinal changes. We'll look at those. Latitudinal changes. As it gets warmer, species will migrate north, such as beech trees. Beech trees are a big part of hardwood forests all over the eastern United States. Future scenarios, depending on the scenario, have, no matter how you slice it, beech forest or beech comprising major parts of forests migrating northward as climate warms. What will replace the beech? Various types of oaks or other warmer climate species presumably will be replacing the beech and others that are migrating northward, and eventually the boreal forest is probably going to migrate slightly northward. And this has impacts for ecosystems, especially because the rate of change is very fast. We humans are accelerating climate warming faster than many natural systems have had to respond previously during natural cycles of glaciation, interglaciation, warm periods, cool periods. We are heating it up really fast, so the rate is important. So, yeah, altitudinal changes. Current climate, or perhaps recent climate, future climate, one with very high increase in temperature and an increase in precip will take an ecological niche like montane steppe and bring it to a higher elevation, and alpine white tundra to a higher elevation. In some cases, certain ecological niches may disappear, get driven right off the top of the mountain. So we need to think about warming affecting species distributions both latitudinally and elevationally, or altitudinally in terms of the altitude in areas with topography. The pika or pika, this little species here lives on the flanks of mountains in places like the Northern Rockies, and is very keyed into certain ecological parameters: precipitation, temperature, foraging, and are very susceptible and have locally certain populations have gone extinct because of warming and because of other predators coming in and food sources altering. Thinning of Arctic sea ice is a critical problem, one that in part is tied into the polar vortex. They're all part of the reality that the poles are warming much faster than the rest of Earth. And thinning of Arctic sea ice is obviously important consideration for habitat, important consideration for albedo. The less sea ice there is, the more heat will be absorbed up in this region. So that is an impact of climate change that is happening. Sea ice is decreasing, and it is something that many climate scientists are very concerned about. And again, it's empirical. You can measure it. It's not hard to measure sea ice and how much there is. And it's not hard to understand the importance of sea ice as habitat and as something with much higher albedo than the sea water that is exposed when sea ice melts. Other considerations from polar regions or cold climates is the instability of permafrost. This study done by U.S. Geological Survey on probability of encountering permafrost within 1 meter of the ground surface. In much of Alaska, much of Siberia, much of parts of northern Canada, you dig down 1 meter and you find ice. Solid ice that is, maybe it melts down a little bit in the summertime and then reestablishes itself in the wintertime. And this is 2010. So very low probability down here in the Alaska, the Aleutians, the peninsula, that's the warmest part of Alaska. We can see, though, that parts of interior Alaska with relatively high probability of finding permafrost within 1 meter of the surface, you see that probability decreasing. And that probability is already a reality in places where melting ice in the soil in the subsurface has caused structural damages, roads, infrastructure, and this would just be a picture of the landscape that we're talking about. This is summertime and there's some melting going on. As summers get warmer and winters are less cold, the reality is there is a lot of organic matter trapped in these soils that would be much better retained in these soils than getting oxidized and put into the atmosphere as CO2 or just directly seeping into the atmosphere, diffusing into the atmosphere as methane. So keep those frozen, keep the ice fields frozen, keep the permafrost frozen. We really can't afford to go into a scenario like this. More empirical evidence. This just came out this week, I think, this paper um, in the journal Science. Pervasive ice sheet mass loss reflects competing ocean and atmospheric processes, kind of like a brutally dense 4-page science article with some figures. But what they show is red is net melting, blue is net gain, and red is melting. So, and what we're doing here is traveling around the perimeter of Antarctica from the Bellingshausen Sea to Amundsen Sea to Ross Ice Shelf over here to Wilkes Land, Amory, Queen Maud Land, and back around. So we're just taking a trip around the island and stretching it out here. And what we can see is that there's more loss of ice than there is gain of ice. There are places, parts of the Ross Shelf, are seeing some small gains in the amount of snow or ice. But most of the perimeter of Antarctica is showing losses of ice, thinning ice, loss of mass of ice, and the same is true, and even more so in Greenland. So if you're interested in the details of this kind of climate science, just type these words into your browser and you can find this article in the journal Science, and you can download the PDF for free. Also considering polar or high latitude regions, we talked about fundamentals of the climate system and the critical role that oceans have. And one of the critical aspects of ocean circulation is the reality that warm ocean water migrates northward from the mid-Atlantic. At the surface, there's a Gulf current that migrates northward as well, carrying warm water and warm air northward. That eventually sinks and then returns in the subsurface in this deep circulation system. Cold water finally rises back up and then warms and is warming more than normal, causing more intense monsoons. Part of what drives this system is the formation of ice up here that makes the water more dense, more salty, and causes it to sink. Melting of ice and the less formation of ice put this entire conveyor belt system at risk of weakening. Meaning, eventually, like the British Isles might become as cold as, let's just go to where is their equivalent latitude in North America, Hudson Bay. The only reason that I think Paris is farther north than we are here down in Vermont. Or comparable latitude for sure. So the climate of northwestern Europe is strongly dependent on ocean circulation, which is strongly dependent on having a cold climate that drives this part of the system. Ocean acidification, which maybe if you're a geochemist you might prefer to it be called increasing or decreasing ocean alkalinity. We talked about that already. But whatever the case, increasing partial pressure of CO2 in the atmosphere causes CO2 to dissolve to a greater extent in seawater. So that's what's represented here, the dissolution of CO2 from atmosphere into seawater. It makes carbonic acid, which lowers the pH of ocean water. And lowered pH of ocean water inhibits calcification. The more saturated with aragonite seawater is, the better the conditions for calcifying organisms, reefs, mollusks, all kinds of shelly organisms that build their shells from seawater, from dissolved calcium and bicarbonate in seawater, require that saturation levels be high, that the oceans not be acidic, basically. What we see marching forward from 1765 to 1995 is a slight decrease in the aragonite saturation levels. As we march forward in the 21st century, the oceans become increasingly less alkaline or more acidic, and the aragonite saturation levels get not only dangerously low, but at a level where marine ecosystems are going to crash. Policymakers pay attention to this one because the entire, really, like the basis of marine life is the fact that aragonite saturation levels need to be maintained somewhere like what it looked like in the 20th century or the 18th century. It can't look like what these models are predicting if CO2 emissions are to continue to increase and we are not able to fix CO2 out of the atmosphere. So we got to figure this out. A case study, a laboratory study done to show the effects of ocean acidification. same reaction. And what is shown here actually is a plot from 1940 to 2017 or so, showing atmospheric CO2. Here it goes. It hadn't quite reached 400 by the time this study was done. Also shown is the partial pressure of CO2 in seawater. It's increasing. Why is the partial pressure of CO2 in seawater increasing? Well, we could bring up the old carbon cycle diagram again and show the fact that the atmosphere has far more CO2 in it than it did decades earlier. And by Henry's law, the laws of nature, that is going to force more CO2 into the oceans, and that is going to decrease the pH of the oceans. And you might say, oh, the pH of the oceans will only decrease from 8.15 to like 8.05. That's about what the decrease has been. But the pH scale is a log scale, so that means a 30% decrease in the pH of the oceans. It about parallels the 30% increase in the amount of CO2 in the atmosphere. And increased acidity in the oceans or decreased alkalinity or decreased aragonite saturation means that nice shells like this eventually start to dissolve or not be able to form themselves. This is a sea butterfly. It's a shell placed in seawater with increased acidity, and it slowly dissolves over 45 days because it needs the alkalinity of seawater. It needs the high dissolved calcium and bicarbonate and not a lot of dissolved CO2. Temperature dependence of CO2 solubility in seawater. So as temperature goes up, the solubility of CO2 in seawater goes down. So eventually the oceans, as they warm, are going to start losing CO2 back to the atmosphere. So far, the oceans have served as a sink for approximately half of anthropogenic CO2 emissions. And it is being stored in the oceans, and it's causing the oceans to acidify a bit. But it's also keeping it from the atmosphere, where it's an infrared active agent that warms the atmosphere. So either way, got to suck it out of the atmosphere, suck it out of the oceans, and put it in terrestrial systems or in the crust of the earth or somewhere. It's got to get it out of the ocean and get it out of the atmosphere. Tired of saying this. Changes in runoff in the Alps. Alpine regions are being affected. Historically, snowmelt used to occur later in the season. This is January 1st, January 31st, February, March, April, May, June. July. Snowmelt used to deliver more water later and longer into the summertime than happens now, than is predicted to happen under future scenarios. So this is 1960 to 1990. In many places, the shift has been observed. We look at this in water resources class, how less snowfall in many mountain regions and more rapid snowmelt means changing water resource budgets in the foothill regions surrounding the mountains. Look at Tajikistan. Formation of freshwater resources in Tajikistan, so tied into glaciers and snowfield. Peru in South America, so tied into glaciers and snowfields. And if those glaciers and snowfields disappear, there goes the water resource. So speaking of water resource stress, multi-year droughts, decreased precipitation, drying up rivers, the Hwanghae River drying up, health problems due to arsenic and fluoride in groundwater in India. We've looked at that, not so much related to climate change, but certainly a water stress. Multi-year droughts in the western United States that have caused precipitous declines in water levels in aquifers. Press pause and look around if you want to look at the details. Flooding, climate-related floods often can cause outbreaks of disease. Malaria range is expected to increase. Are we going to have to use DDT to kill mosquitoes because malaria is all of a sudden spread up into Canada? Depends on what we choose to do as a global society about CO2. Agricultural yields. Might some parts of the world see increases in agricultural yields? Sure. Perhaps parts of Canada, northeastern United States, perhaps parts of East Asia that are going to warm, but also critically sensitive parts of the world are going to see diminished agricultural productivity, longer droughts, more unpredictable rainfall. Solutions. Let's think about it. We can reduce emissions. And sure, we have solar now, we have wind, we have hydroelectric, we have electric vehicles, hydrogen fuel cells, geothermal energy. These are tons of CO2, metric tons of CO2 emitted annually from fossil fuel use and cement production. When you make cement, you drive CO2 off out of the CaCO3. So that's like 10% of global CO2 emissions. But most of the driver here is, in spite of solar, wind, electric, we have not really gotten our heads around decreasing emissions. And we must decrease the emissions. But we're not on target to do so very well yet. The other thing to deal with this problem is to sequester carbon out of the atmosphere and then pull it out of the oceans and fix it into ecosystems. We can look at world biomes and potential for carbon storage, and many ecosystems have very high potential for carbon storage. Whole part of the eastern U.S., not too bad. You're thinking about forest carbon in lab. Are there ways to take advantage of photosynthesis and decomposition to store soil carbon, to sequester carbon from the atmosphere and soils through agriculture, through forestry, perhaps through algae that are engineered in some way to grow fast, that fix carbon out of the atmosphere? There are geological means too. So you can read about this in some of the summaries that you have access to for class this week. Carbon sequestration potential of agroforestry is very high, especially depending on the region. Soil organic carbon that is in cropland soils. Tons of carbon per hectare. This would be tons of carbon for 2 acres if you use American terms. There's a large amount of soil stored. There's a lot of potential for storage of carbon in soils if we manage them properly and if it becomes a concerted effort. You can see forest management here, grazing management. So there's a lot of ways that carbon can be fixed and stored in soils. Part of the New Perennials project is a big focus of the New Perennials project is retooling agriculture, redefining, rethinking agriculture to use soils as a reservoir of carbon, to fix soils intentionally, to fix carbon intentionally in agricultural soils. Carbon sequestration, there's carbon capture and storage. We heard presentations about CCS associated with coal, capturing the CO2 emissions right there on site and injecting it into deep geological reservoirs. There's geologic sequestration that involves trying to accelerate natural mineral carbonation reactions, either weathering reactions, and then storing the new minerals that form that have carbonates in them, that store the CO2 as either dissolved or liquid or in solid form. There are some ideas of ocean sequestration, but I don't think that's very practical. Terrestrial sequestration, forest lands, ag lands, biomass croplands, restoration of degraded lands for fixing carbon, retaining carbon in managing boreal wetlands and peatlands, retaining carbon in the gelisol permafrost soils of the far north, all critical as part of the multi-pronged approach needed to fix carbon out of the atmosphere and into soils or the lithosphere. This is the Belvedere Mine in northern Vermont. My colleague John Kim, former student Levi Doria, we did a study on the carbon sequestration potential of the old magnesium silicate mine tailings from an asbestos mine in northern Vermont. There's a lot of potential for, if enough technological research were to be invested in mineral sequestration of carbon dioxide, there are many old mines that could serve as sites for intentionally fixing CO2 back into minerals, lithospheric type material, earth materials, rather than atmosphere. This is a Department of Energy schematic that shows how that works. You take a magnesium silicate mineral, you take CO2. That CO2 may be coming from some kind of power plant, and the CO2 is reacted with the mineral and turned into a mineral powder rather than going into the atmosphere. The primary challenge is that it's currently not economically viable. Our economic system does not foster or favor the investment in this kind of process. It is theoretically feasible. The problem is it's kinetically not favored because chemical weathering just naturally happens very slowly. The reaction of CO2 with minerals happens over timescales of thousands to millions of years normally. So how do we accelerate the process? Yeah, there's no mine tailings. Mine tailings waiting to be reacted with CO2 from the atmosphere or fixed from some other power source, biomass plant or something. And reacting the CO2 with these waste materials to fix them into the crust, the lithosphere, to store them away. Yeah, the site is up in northern Vermont. Geologic map of Vermont. I'm a geologist, got to throw in a geologic map here or there. All along this central belt of rocks in Vermont are serpentinites, ancient oceanic rocks, deep crust, actually from the mantle of the earth, that are pretty reactive with CO2. And where we go forward depends on emissions for sure, and this is ppm CO2 equivalent, because it also includes maybe a little methane or whatever, but we're thinking about converting everything to CO2 equivalents. Currently, we are 415 ppm CO2, and then you convert the others and you end up with like an equivalent. Right now we're at around pushing 500 CO2 equivalents when you convert the methane and CFCs and so forth. All these different pathways depend on emissions. And even if we take the lowest emissions pathway, we're still up in the 400 plus ppm range until the end of this century. The only way we really start to decrease is if we fix carbon intentionally out of the atmosphere. So it's got to be emissions reductions, and it's got to be fixation, sequestration, carbonation, etc. Last video slide. As I look at this slide, I think about solutions. I think about one of the world's largest solar installations in the world, making electricity in Thailand, emitting no CO2 to the atmosphere as it makes the electricity. But it also has altered the land. This is no longer agricultural land or whatever it was before. It's no longer native tropical forest, perhaps. So there's those considerations. There's always trade-offs. I look at the soils of this landscape in Thailand, and I think about the carbon sequestration potential of these soils. I think about how these forests are being managed, and I wonder if they're being managed to maximize sequestration of carbon. I think of Thailand, and I think of a country that has less economic resources than much of the, quote, developed world, and yet I see encouraging signs of sustainable energy development in parts of the world that have a right to more energy. I see also the need to avoid the uneven, unjust impacts of climate change by doing everything possible using our scientific and technological knowledge to reduce CO2 emissions and to increase conscientiously, with knowledge of the natural world, fixing CO2 out of the atmosphere. It's all complicated, and it will not be an easy path, but the solutions are there. And as Liu et al. Said early in the semester, often there are lags, and we are lagging as a global society in our response to climate change. But sometimes we cross thresholds, and we need to cross a threshold into a new world of where everybody, every Republican, Democrat, Republicano, socialist, conservative, everybody is on board with solving what is bound to impact everybody in some way, climate change. So I leave you there. I leave you with 15 interesting case studies that have been summarized down into 2 concise pages, many of which get into some interesting case studies of climate change solutions, approaches, conserving biodiversity in an age of climate change, ecosystem services as a function of climate change. So I wish you all well and sign off for now.